Hi everyone, my name is Sri Chandra and today my topic is fine-grained activation for power reduction in DRAM. Let's get into the topic introduction. DRAM has been the ubiquitous solution for memory in all types of systems from the world's fastest supercomputer to the latest mobile smartphones. Its widespread adoption is due primarily to device standardization, particularly the package input, pinout, and the device operating protocol. Unfortunately, standardization also tends to inhibit dramatic or, in many cases, even moderate modifications. Consequently, evolution in DRAM technology comes in small, incrementally steps. In this article, we discuss on optimization to the DRAM device architecture that requires no modification in protocol and a low-cost modification in logic control that doesn't affect the device interoperability with standardization memory controllers and interfaces. Modern DRAM architecture. Since the 1970s, DRAM devices have used a split addressing mechanism that divides the target address into two components, allowing a narrow and thus inexpensive address bus. The DRAM array consists of rows and columns that are accessed and addressed using separate commands, which typically arrive several clock cycles apart. Data in the array is represented as charge stored in capacitors and must be sensed before it can be read or written. The act of sensing the charge is called an activation and is performed upon receiving a row address strobe RS command. Activations are always performed on an entire DRAM row simultaneously. Once an activation is completed, the data remains within the senses amplifiers to be written or read with either a CAS or CASW command, respectively. After reading or writing data, the memory controller that prepares the DRAM array for the next activation via pre-charge operation, one of the which is always paired with previous activation. Activation and pre-charge operation always applied to the data array's entire rows, regardless of how much data is actually needed. In a typical DRAM device, a row of the data array has 8192 bits in a column. The addressable portion of the row is typically between 4 and 32 bit. In modern DRAM devices, the storage array isn't a monolithic structure, but rather consists of thousands of smaller cores, typically 256 kbits apiece. The prevents having word a bit line the span the entire array length, which would represent necessarily large loads. Although these course architecture and organization vary between manufacturers, the concept spans all DRAM's devices because it's a physical necessity. This concept shouldn't be confused within the multiple independent arrays in modern devices called banks. A typical DRAM device has 4 or 8 banks, which allow requests to be handled in a parallel, thereby reducing conflicts and allow increased bus utilization. The DRAM protocol also includes a refresh command. Due to the nature of the capacitors used to store individual bits of data, the representative charge leaks channels a group of one or more banks of DRAM that handles requests from the memory controller. These banks operate independently from other channels. Due inline memory module DIMM, a printed circuit board containing individual DRAM devices grouped together to form one or more ranks of memory. The average consumer is most familiar with the formation of DRAM. Rank, a group of DRAM devices operating together to service requests from the memory controller. Each device shares the same command and address bus, but each of these devices data buses are grouped to form a larger monolithic data bus. A JEDC standardization memory system is organized by banks that operate on a 64-bit data bus. Bank, an independent array of DRAM cells inside a DRAM DRAM, DRAM the device. A typical DDR3 DRAM device has 8 banks row, a group of bits in the DRAM array that are sensed and pre-charged together. When receiving an activate or pre-charge command, respectively, a typical DDR3 DRAM device has 16,384 rows. Column. The smallest addressable portion of the DRAM device, depending on the DRAM device, the column can arrange from 4 to 16 bits and even has high as 32 bits for high-end graphics memory. You can see the figure a element of modern memory system. The modern DRAM device architecture, a large array of capacitance is addressed with a row and column decoder. The address bits are sent to the sense amplifier, which data may be read or written. Power consumption in DRAM system. DRAM power dissipation is all application specific. The usage pattern in the memory system determines the ratio of the three components. Under light use, the background power dominates the total power dissipated. Conversely, under heavy use, the activation power is the most dominant. The total read or write burst power consumption depends on both the memory system activity and the burst length. For example, in a system with 24 GHz processor and single rank of typical 400 MHz, DDR2 DRAM 800 Mbps vary. The total cache size and cache block size will quickly the executing the quick benchmarks demonstrate how different loads on the memory system impacts the breakdown of power consumption within the DRAM. A larger cache size reduces the load on the memory system, leading to fewer activations and more opportunities to place the DRAM device in power down modes, thereby reducing the background power as well. A large cache block size provides similar benefits to increasing cache size and also amortize the high cost of DRAM row activations over more read and write data transfers. The relative effects of various cache configurations are application dependent. Although the quick benchmarks results suggest that cache block size has a greater impact on power consumption than total cache size, the art benchmarks results shows the opposite. There is no ideal solution for the all situations. Figure 3, cache configuration on and the impact on power components in the memory system. For a 2.4 GHz CPU, executing the quick benchmarks and the art benchmarks. The quick benchmark results suggest that cache block size has a greater impact on power consumption than total cache size, but the art benchmark results suggest the opposite. Binary activation with the posted CAS command. Successively, generations of the DDR standard have introduced increasingly complex commands to account for higher clock frequency and complex scheduling algorithm. The second generation DDR protocols introduced the post CAS command. To implement this commands, additional logic on the DRAM device buffers the column address and the delay the commands until the row has been completely activated. The TAL timing parameter controls the timing delay. When using the posted CAS command, the memory controller sends the RAS and CAS command in successive clock cycles instead of waiting until the row has finished activating to execute the CAS command. This scheme simplifies the memory controls, but command bus scheduling by combining the activation column access and pre-charge operations into two adjacent clock cycles. Although the mechanism was initially implemented for scheduling purpose, there are other benefits from early access to the column address. As we mentioned earlier, current memory systems must activate an entire row of the data array before any access is possible, regardless of how little of the row is actually required. However, we using the CS command, the column address is available near the beginning of for an activation. Thus, the device can select a smaller portion of the row to activate, thereby reducing the power dissipated by both activation and pre-charge operations. Because the command and logic already exist to send and buffer the column address, no modification to the protocol bus or memory controller are necessary. The architecture modification includes the addition of a single one hot decoder and a small amount of control circuitry for each selectable division in the data array. The decoder uses the column address to select only the required portion of the row. The higher the degree of the decoder and finer the grain of access allowed to the row in the data array. Although it's possible to activate the individual column containing in the request or experiment suggested, there will be dimensioning returns from after decoder size of 5 to 32. Beyond this point, the decoder cost with outweigh the overall power reduction. Thanking you. I conclude my here. I'll completing my presentation. Thanking you all.